Hi, everyone. Thanks for coming today to see our talk. My name is Daniel.
My name is Nikhil.
And I'm Nick.
And today, we're very happy to talk about JavaScript. All right. So if you're in the world of machine learning, if you're doing training a model or anything about machine learning, you're most certainly dealing with Python, right? And for a good reason. Python has been one of the mainstream languages for scientific computing for the last decade. It has a lot of tools. But it doesn't have to be that way. It doesn't have to end there. Today, we're here to convince you that the browser and JavaScript have a lot to offer to the world of machine learning. And TensorFlow Playground is a great example of that. How many people here have seen this visualization? Quite a few. I'm glad. For those of you that haven't seen it, TensorFlow Playground is in-browser neural network visualization, shows you what is happening inside the neural network as the network is training. And when we released this was kind of a fun, small project. When we released this, it had a tremendous success, especially in the educational domain. And even today, we're getting emails from high schools and universities around the world thanking us for building this. And they're using it to teach students, beginners, about machine learning. When we saw the success of TensorFlow Playground, we started wondering, why is it so successful? And we think the browser and JavaScript have a lot to do with it. For one thing that's very special about the browser, it has no drivers and no installations. You can share your app with anyone, and all they have to do is click on a link and see your application. Another important thing about the browser is highly interactive. In the Playground app, we have all these controls, drop-down controls that you can change and quickly run different experiments. Another nice thing about the browser, it runs on laptops, it runs on mobile devices. And these devices have sensors, like the microphone and the camera and the accelerometer, and they're all behind standardized web APIs that you can easily access in your web app. We didn't take advantage of this in the Playground, but we'll show you some demos later. And most importantly, when you're building web apps, these apps run client-side, which makes it easy to have the data stay on the client and never have to send it back to a server. You can do processing on device. And this is important for privacy. Now, to come back to the Playground example, the library that powers this visualization is not TensorFlow. It is a small neural network library, 300 lines of JavaScript code. We wrote for this visualization, and it wasn't meant to be reusable or to scale for bigger neural networks. But it became clear to us when this became so successful and popular that we should go on and build such a library. And we went and built DeepLearn.js. We released it August 2017. We figured out a way how to make it fast and scale by utilizing the GPU of laptops and cell phones through WebGL. For those of you that are not familiar, WebGL is a technology originally meant for rendering 3D graphics. And the library that we built allows for both inference and training entirely in the browser. When we released DeepLearn.js, we had an incredible momentum. The community went instantly with it and took pre-trained models from Python and ported it in the browser. One example I want to show you of that is the style transfer demo. Someone went and took the pre-trained model, and this demo has an image, a source image on the left, an artist on the right, and then it can mash them together. And they made this in a creative, interesting application. Another demo is people would take models that read a lot of text, and then they could generate new sentences. And then they ported it in the browser and explored novel interfaces, how you can explore all the different endings of a sentence. In the educational domain, people took the standard convolutional neural nets and built this fun little game where you can train your own image recognition model just by using the webcam. And this was very popular. And lastly, researchers took another example. They took a font generation model that can generate new fonts. Previously, it was trained on a lot of font styles. And then they built this novel interface in the browser, highly interactive, where you can explore different types of fonts. Now, building on that incredible momentum we had with DeepLearn.js, about a month ago at the TensorFlow Dev Summit, we announced that we are joining the TensorFlow family. And with that, we introduced a new ecosystem of tools and libraries around JavaScript and machine learning called TensorFlow.js. Now, before we dive into the details, I want to go over 3 main use cases of what you can do with TensorFlow.js today. You can write models directly in the browser. We have sets of APIs for that. You can also take pre-trained models that were trained in Python or other languages and then port them for inference in the browser. You can also take these existing pre-trained models and retrain them, do transfer learning right there on device. To give you a schematic view of the library, we have the browser that does all the computation using WebGL. TensorFlow.js has 2 sets of APIs that sit on top of this. A core API, which gives you low-level building blocks, linear algebra operations like multiply and add. And on top of it, we have Layers API, which gives you high-level building blocks and best practices to build neural nets. And on top of that, because there's so many models written in Python today, we offer tools to take an existing model, a Keras model, and a TensorFlow Safe model. These are 2 formats that are very popular server-side. And these tools will automatically convert that model to run in the browser. Now, to give you an example of our core API, I'm going to show you, we're going to go over code that tries to train a model that fits a polynomial curve. And we have to learn the 3 coefficients A, B, and C. Now, this example is pretty simple, but the code walks you through all the steps of how you would train such a model. And these steps generalize across different models. So we import TensorFlow for TensorFlow/TensorFlow.js. For those of you that are not familiar, this is a standard ES6 modern JavaScript import. We have our 3 variables that we're trying to learn, A, B, and C. We mark them as variables, which means that the optimizer, the machinery that runs and trains our neural network, can change these variables for us. We have our function, f of x. Given some data, it will compute the output. This is just a polynomial function, quadratic function. On top of the standard API like tf_add and tf_multiply, we also have a chaining API. Chaining has been very popular in the JavaScript world, so you can call these methods, these mathematical methods on the tensor itself. And this reads better, closer to how we write math. So that's our model. To train it, we need a loss function. And in this case, we are just measuring the distance between the prediction of the model and the label, the ground truth data. We need an optimizer. This is the machinery that can optimize and find those coefficients. We specify a learning rate there. And for some number of epochs passes over our data, we call optimizer.minimize with our loss and our f of x and y's. So that's our model. Now, this is clearly not how everyone writes machine learning models today. Over the years, we've developed best practices and high-level building blocks, and new APIs emerged, like TF layers and Keras, that makes it much easier to write these models. And for that, I want to walk over our layers API to show you how easy it is. We're going to go through a simple neural network that sums 2 numbers. But what's special about this network is that the input comes as a string, character by character. So 90 plus 10 is the input to this network being fed as a string. And the network has an internal memory where it encodes this information. It has to save it. And then on the other end, the neural network has to output the sum, 100, again, character by character. Now, you might wonder why go through such a trouble to train this neural network like this. But this example forms the basis of modern machine translation, and that's why we're going over this. To show you the code, we import TensorFlow from TensorFlow.js. We have our model. We say tf.sequential, which means it's just a linear stack of layers. The first two layers, I'm not going to go into details, but those two are building blocks that can take these strings into a memory, into an internal representation. And the last three layers take this internal representation and turn it into numbers. And that's our model. To train it, we need to compile it with a loss, an optimizer, and a metric we want to monitor, in this case, accuracy. And we call model.fit with our data. Now, one thing I want to point out about model.fit, training can take, for this example, it can take 30 or 40 seconds in the browser. And while that's running, we don't want to block the main UI thread. We want our app to be responsive. This is why model.fit is an asynchronous call, and we get a callback once it's done with the history object, which has our accuracy as it evolved over time. Now, I went through examples of how you write these models in the browser. But there is also a lot of models that have already been written in Python. And for that, we have tools that allow you to import them automatically. Before we dive into the details, I want to go through, show you a fun little game that our friends at Google Brand Studio built called Emoji Scavenger Hunt. And this game takes advantage of a pre-trained model of a convolutional neural network that can detect 400 items. And I'm going to walk over to a Pixel phone and open up a browser, just to show you that TensorFlow.js can also run in a browser, because we're using standard WebGL. And I'm going to ask here Nikhil on my right to help me out here, because I'm going to need some help. Now, to give you some little details about the game, it shows you an emoji, and then you have to go with your camera, run around your house, and find the real version item of that emoji before the time runs out. And there is a neural network that has to detect that. All right, shall we start? All right, let me see. We're going to play it here live. All right, we have to find a watch for 20 seconds.
A watch.
All right, that's great. Woo! All right, let me see what's next. All right, we need a shoe. Come on, Nikhil.
Got a shoe.
Thanks, buddy. Yay.
Right.
Let's see what our next item is. Banana. We have 30 seconds to find a banana.
Does anyone have a banana? Anyone have a banana? Oh, awesome. We got a banana over here.
Thanks, man.
Here we go.
All right.
Awesome.
All right, so our high score is going up. Let's see what our next item is. Beer.
Beer. Daniel, it's 12:30 in the middle of I/O. Let's get back to the talk, man.
All right, man.
All right, so let's talk a little bit about how we actually built that game. Switch back to the slides here. OK, so what we did was we trained a model in Python to predict from images 400 different classes that would be good for an emoji scavenger hunt game. These are things like a banana, a watch, and a shoe. The way we did this was we took a pre-trained model called MobileNet. And now, if you don't know what MobileNet is, it's a state-of-the-art computer vision model that's designed for edge devices. It's designed for mobile phones. So what we did is we took that model and we reused the features that were learned there, and we did a transfer learning task to our 400 class classifier. So then, once we do that, we have an object detector. So this object detector lives entirely in the Python world. So the next step of this process is to actually take that and convert it into a format that we'll be able to ingest in the web, and then we'll skin the game and add sound effects and that kind of thing. So let's talk a little bit about the details of actually going through that process. So in Python, when we're actually checkpointing and training our model, we have to save it to disk. So there's a couple ways you do this. The common way with TensorFlow is to use what's called a saved model. Details are not important for this talk here, but the idea here is that there are files on disk that you need to write. Daniel also mentioned that we support importing from Keras. Now, Keras is a high-level library that lives on top of TensorFlow that gives you a sort of higher-level API to use these things. Details unimportant. There are also files on disk that it uses to checkpoint. All right, so we have a set of files, And now the next step is to actually convert them to a format that we can ingest in a web page. So we have released a tool on pip called TensorFlow.js. Inside of that tool, we have some conversion scripts. All you do is run this script. You point it to those saved files that you had on disk, and you point it to an output directory, and you will get a set of static build artifacts that we'll be able to use on the web. The same flow holds for Keras models. You point to your input h5 file, and out pops a directory of static build artifacts. All right? So you take those static build artifacts, and you host them on your website. This is the same way you would host PNGs or CSS or anything of that sort. All right, so once you do that, we provide some APIs in TensorFlow.js to load those static build artifacts. So it looks something like this. For TensorFlow save model, we load the model up, and we get a model object back. That model object can actually make predictions with TensorFlow.js tensors right in the browser. The same flow holds for Keras models. We point to those static build artifacts, and we have a model that we can make predictions on. OK, so under the covers, there's actually a lot going on. When we convert these files to a format that we can ingest in the web, we actually are pruning nodes off of that graph that aren't needed to make that prediction. This makes the network transfer much smaller and our predictions much faster. We're also taking those weights and sharding and packing them into 4 megabyte chunks. This means that the next time the browser loads that page, your weights will be cached, so it's super snappy. We also support about 90 of the most commonly used TensorFlow ops today, and we're working hard to continue supporting more. And on the Keras side, we support 32 of the most commonly used Keras layers during that importing phase. And we also support training and evaluation of those models, so computing accuracy once you get them in. Of course, you can also make predictions as well. All right, so I want to show you a demo before I bore you anymore. This demo is built by our friends at Creative Lab as a collaboration between them and a few researchers on Google Brain. So I'm going to go back over here to this laptop. OK? So the idea of this model is it takes a 2D image of a human being, and it estimates a set of key points that relate to their skeleton. So things like your wrist point, the centers of your eyes, your shoulders, and that kind of thing. So I'm just going to turn the demo on here. So when I do that, the webcam will turn on, and it's going to start predicting some key points for me. And I'm going to step back here so you can actually see the full thing. And as I move around, you'll see the skeleton change and make some predictions about me. All right, so there's obviously a lot you can do with this. We're really excited to show you a fun little demo. It's very thin. And what's going to happen is when I click this slider, we're going to move to a separate mode where it's going to look for another image on the internet that has a person with the same pose as me. OK? Let's turn that on. Is it going to work here? Of course, it's not working now. OK, well, we have a physical installation of this, which you can go check out. It's at the experiments tent on H. And it's really fun. It's a full screen version of that where you can see another version of you. We have released this model on NPM, so you can go and use this, and you need no machine learning experience to do it. The API lets you point to an image and out pops an array of key points. It's that easy. So we're really excited to see what you do with that. OK, so there's a lot you can do with just porting the models to the browser for inference. But since the beginning of DeepLearn.js and TensorFlow.js, we've made it a high priority to be able to actually train directly in the browser. This opens up the door for education and interactivity, as well as retraining with data that never leaves the client. So I'm going to actually show you another demo of that back on the laptop over here. OK, Daniel, you want to come help me? Here we go. Cool. OK, so the game is in 3 phases. In phase 1, we're going to actually collect frames from the webcam. And what we're gonna do is we're gonna use those frames to actually play a game of Pac-Man. Okay, so Daniel, why don't you start collecting frames? What he's going to do is he's going to collect frames for up, down, left, and right. And those are going to be associated with the poses, with the 4 controls for the Pac-Man game itself. So as he's collecting those, we're saving some of the images locally, and we're not actually training the model yet. So once he's done actually collecting those frames, we're going to train the model. And again, this is going to be trained entirely in the browser with no request to a server anywhere. OK, so when we actually train that model, what's going to happen is we're actually going to take a pre-trained MobileNet model that's actually in the page right now, and we're going to do a little retraining phase with data that he's just collected. So why don't you press that train model? Awesome. Our loss value is actually going down. It looks like we've learned something. OK, so the phase 3 of this game is to actually play. So when he presses that button, what's going to happen is we're going to take frames from that webcam, and we're going to make predictions given that model that we just trained. Why don't you press that play button, and we'll see how it goes. So if you look in the bottom right of the screen, you'll actually see the predictions happening. So it's highlighting the control that it thinks it is, and you'll see him actually playing the Pac-Man game now. So obviously, this is just a game, but we're really excited about opportunities for accessibility. You can imagine a Chrome extension that lets you train a model that lets you scroll the page and click. Now, all of this code is online and available for you to go and fork and build your own applications with, and we're really excited to see what you do with it. All right, man, we got to get back to the talk.
All right.
OK, so let's chat a little bit about performance. What we're looking at here is a benchmark of MobileNet 1.0 running with TensorFlow Python. This is classic TensorFlow, not running with TensorFlow.js. We're thinking about this in the context of a batch size of 1. And the reason that we want to think like that is because we're thinking of an interactive application like Pac-Man, where you can only read 1 sensor frame at a time, so you can't really batch that data. On the first row, we're looking at TensorFlow running with CUDA on a 1080 GTX. This is a beefy machine, and it's getting about 3 milliseconds per frame. And I want to mention that the smaller the bar, the faster it is. On the second row, we're looking at TensorFlow CPU running with AVX2 instructions on one of these MacBook Pros here. We're getting about 60 milliseconds for a frame there. All right, where does TensorFlow.js fit into this picture? Well, it depends. So running on that 1080 GTX, that beefy machine, we're getting about 11 milliseconds for a frame. On TensorFlow.js running on an integrated graphics card on one of these laptops, we're getting about 100 milliseconds per frame. I just want to point out that 100 milliseconds is actually not so bad. That Pac-Man game was running with this model, and you can really build something interactive with that. The web is only going to get faster and faster. There are a new set of standards like WebGL compute shaders and WebGPU, which gives you much closer to the metal access to the GPU. But the web has its limitations. You live in a sandbox environment, and you can only really get access to the GPU through these APIs. So how do we scale beyond those limitations? With that, I'm going to hand it off to Nick, who's going to talk about how we'll scale.
Thanks, Nikhil. Today, we're launching TensorFlow support for Node.js. Thank you. We're really excited to bring an easy-to-use, high-performance machine learning library to JavaScript developers. The open source community around Node.js and NPM is really awesome. There's incredible movement in the space, a ton of libraries and packages for developers to use today, and now we're bringing ML to this front. The engine that runs Node.js, V8, is super fast. It's had tons of resources put into it by companies like Google, and we've seen the interpreter be up to 10 times as fast as Python. Lots of room for performance improvements. Also, using TensorFlow gives us access to really high-end machine learning hardware like GPU devices and TPUs in the cloud. Look for support for that soon. Let's step back and look at the architecture we highlighted earlier. We have a layers API and then a little bit lower level core API that has our ops. This whole runtime is powered by WebGL in the browser. But today, through NPM, we're shipping a package that gives you TensorFlow, that gives you access to those TPUs, the GPU, and CPU. All of this is through our NPM package. To show you how easy it is to use our node bindings, I wanted to show you a little code snippet. This application function right here is a very common server-side request response handler for an endpoint. Those who have worked with the Express framework know exactly what's going on here. Our endpoint listens for /model and takes input as a request, which we pass into a TensorFlow JS model, and that output is pushed out into the response. Now, to turn on high-performance TensorFlow code, we only need 2 lines of code. An import, which loads our binding, and then an existing API call to set our backend to TensorFlow. Now this model is running with the performance of TensorFlow. What works today out of the box? So we can take pre-existing Python models and run those natively in Node.js. The models we've kind of showed off today, all of those will run in our Node runtime. There's no need to bring a Python stack to your Node infrastructure, just run it in JavaScript. Our NPM package today ships an off-the-shelf CPU build. There's no additional drivers to do, just install our package and you're up and running. Our whole API we ship in TensorFlow JS will work with our Node runtime. Every API we've showcased will work today out of the box. Now, we've built a little demo using Major League Baseball data in Node.js to showcase what you can do with machine learning, Node.js, and JavaScript. We've used Major League Baseball Advanced Media's pitch effects data set to do some machine learning. The pitch effects data set is this large library of sensor data about pitches that baseball players have thrown in actual baseball games. For those that aren't super familiar with baseball, we've given a little context here. A pitcher will throw different types of pitches to fool the player who's trying to hit this ball. There's pitches that have higher velocities. There's pitches that are a little slower but have more movement. In this example, we've sort of highlighted the fastball, the changeup, and the curveball. Those are all types of pitches. Don't get too hung up about the details of baseball. What we're really trying to solve here is a very classic machine learning problem of taking sensor information and drawing a classification to that. So for that, I'm going to actually showcase this demo. All right. So on one side of my screen, I have a terminal, which I'm going to start my Node application with. And on the left, I have a web browser. We've built this a very simple UI that listens to what our server is doing over sockets. Those who have used the socket.io library in Node know what this interaction is doing. So I'm just going to type Node start my server. And now all through Node, my model is up and running and training. Every time we take a pass through our data set, we report that over the socket to our client. And you can see the blue bar is moving a little bit closer to 100%. That's our model understanding how to tell the difference between a curveball or a fastball. And as you can kind of see, every step, it moves a little bit differently. And our model's having a little bit of trouble at the moment with the fastball sinker, but it's only looked at data for a few passes. The more this server runs, the better it gets at training. So all of this training data we've shown is historical baseball data from 2015 to 2017. I'm going to hit this test live button, and this is going to use, with ease, the Node framework to go out to Major League Baseball, pull in some newer data, some live data, and run the evaluation. So once this data comes in, we're going to see the orange bars, and the orange bars shows how much better we are at predicting data that our model has never seen before. These are live pitches, and we're really good at identifying the curveball and not so great at that fastball sinker still. So let's jump back and continue to look at our next slide. This is the architecture of what we were doing in that demo. We've built a very simple node server that hosts our JavaScript models. And when we hit that live button, it reaches out to Major League Baseball, pulls in that live data, and runs inference on those new pitches. We continuously just report that to any connected clients through the browser. Where does this stack up in performance? So in that training set, we were looking at 7,000 pitches, and we were training every couple seconds 7,000 pitches. So that's an interesting benchmark, but let's actually classify that with the MobileNet benchmark we showcased earlier. So these are the numbers for Python TensorFlow, the GPU and the CPU inference time. So we're just getting started. We've just launched an NPM package. We have a lot of ways to go, but we have some promising early numbers to showcase. TensorFlow with Node.js is exactly as fast as Python TensorFlow. So with that, I'm going to hand it off to Nikhil to wrap up.
Thanks, Nick. Exciting stuff. OK, so let's recap some of the APIs and libraries and tools that we have supported today with TensorFlow.js. We have a low-level API called the Core API, which is a set of accelerated linear algebra kernels and a layer for automatic differentiation. We saw an example of that with the polynomial regression demo. We also have a high-level layers API that encodes machine learning best practices into an API that's much more easy to use. And we saw an example of that with that addition RNN translation demo. We also have showed you a couple ways that you can take pre-trained models from Python via saved model or via Keras models and port those to the browser for inference or doing retraining or computing accuracy. And of course, we also showed you the new Node.js support for TensorFlow.js today. And we're really excited about that. OK, so this project, TensorFlow.js, was not just the three of us on stage here. It was a cross-team collaboration between many amazing people at Google. And we also have some amazing open source contributors that I want to send a shout out to. This project literally would not have been possible without them, so thank you. All of the things that we talked about here today, the demos, all the code is open source on our website, js.tensorflow.org. All of the code is also open sourced on GitHub, github.com/tensorflow/tfjs. We also have a community mailing list. This is a place where people can go and ask questions, post their demos, and that kind of thing. We have some office hours today at 3:30, and we have some office hours tomorrow at 9:30. Which I invite you to come and talk to us in person. And we also have some tents. We have the experiments tent. That's at H. That's where that move mirror demo, the full screen version of that will be. And we also will be at the AI tent as well. So we are really excited to build the next chapter of machine learning and JavaScript with you. Thank you.